Hi everyone, I am Shangquan Sun and I would like to present our CVPR 2024 highlight paper titled Logit Standardization in Knowledge Distillation. We first discuss our motivation. We noticed that the current logic-based KD methods have temperatures shared between teacher and student, also globally consistent for all samples. However, we do not know why the setting holds and could we get better result by assigning dynamic temperatures. Based on our derivation, we find there are two shackles to keep the setting, namely, student logics are restricted unnecessarily. Here are the notations of our derivation. We first derive the source of softmax involving temperature. For classification problem, we can formulate the probability function of student belongs to the solutions of equation 5. It is a constraint maximization entropy problem. The first constraint makes it a probability summing up to 1, and the second constraint defines the scope of the logit. Based on the Lagrangian multiplier, we transform the constraint optimization into a single equation. Then, by taking its derivative to 1, the probability function reduces to the softmax of logit, and the temperature scaling factor is from the multiplier, which does not have explicit restriction on its value. Similar process holds for student, except that we have the third constraint that restricts the scope of student logit by the teacher's logit expectation. The final probability of student also shows softmax with multipliers forming temperature. Since the multipliers do not have a restriction, and thus we can define their values divergent between teacher and student dynamically among samples. But the problem on how to define the values remain. We first write the general softmax function with bias term as and scaling factor bs. We base our derivation on the assumption that a well-distilled student could perfectly mimic teacher. Based on the assumption, we could write for any pair of indices ij the ratio between the probability at the index I and j for student equals to that ratio for teacher. By simplification and under the condition of shared temperatures, we can see that student logit is restricted with a finite bias from teacher logit. The bias has a finite value of their logit mean difference. Their variances are also restricted to be equal. We leverage the format and advantages of this cofunction and propose a Logit standardization. It has advantages like zero mean, finite deviation, and boundedness. With its help, the issue mentioned before is alleviated. Here is the algorithm. It has two parameters, namely a base temperature tau and KD loss weight lambda KD. We also show a toy case that our method helps. In this case, student S1 has closer logit value range to teacher and thus a better KL divergence. However, its prediction is wrong. In contrast, student S2 has a wrong value range and worse KL divergence. However, its prediction is correct and matches the teacher's prediction. The KL divergence here cannot faithfully reflect the quality of student matching teacher. However, by our method, all logit ranges are rescaled and student S2 has a better KL divergence loss than S1, which is in line with their prediction quality. We experiment our preprocess by equipping it to the existing logit KD. This is the results on C500 with student and teacher sharing identical architectures. Our method can consistently improve the existing logit KD methods. Here is the results on C500 with student and teacher having different architectures. Our method also consistently helps. Table 3 shows the results on ImageNet with two teacher and student pairs. Its performance gains remain. We also conduct ablation studies on the base temperature T, tau, and KD loss weight. This is a sample case of logit visualizations. Our method makes the prediction correct and the logit difference small. Here shows the feature visualization on C500. The first row is for the existing logit KD without our preprocess. As shown in the second row, our method helps the separation of features among different classes. This is a supplemental experiment showing its potential to alleviate student and teacher gap. Students cannot produce logits with close range and variance to teacher. Our method, however, can rescale them into a closer range and reduce the gap between their standardized logit.